Welcome back. So we've talked so far about the cell structure and the membrane, the structure of the membrane, and we discussed how things move in blood, and we discussed how the acid-base reactions work, and we need them to be in their non-ionized form. And now we're going to talk that, okay, well, here's the membrane, here's the drug moving in the blood, it got to the membrane. How do drugs pass through the membrane? This is called membrane transport. So we're going to talk about the different ways molecules could pass through the membrane that we learned about in cell structure. So first of all, we have what we call passive transport. Whenever we say passive transport or passive here, it means energy is not being used. The body's not actually using its energy, or it's not burning energy to allow this transport to happen. Okay, so under passive transport we have a few two examples. We have simple diffusion. Okay, so it says here, okay, so simple, moving down the concentration gradient, so no energy is required, and the carrier is utilized, so system cannot be saturated. So what does all this mean? Well, here's what we're going to explain it here on this picture. Okay, so here is simple diffusion right here. Okay, this is simple diffusion. So I have multiple pictures for you here. Okay, so simple diffusion means, first of all, it's non-ionized, so it could pass through the membrane, and it is moving down the concentration gradient. So that means the force that's pulling the molecule is concentration. So you have a higher concentration of this blue stuff here, lower concentration here, so it's moving from here to here. Okay, if you reverse this, if you make the higher concentration on this side, then it will reverse from here to here. Just so it's following the concentration. The way you want to think of it is, imagine concentration, the differences in concentration, that force is like gravity. Okay, so if I'm on top of a building and I want to throw something down that's going toward the earth, I don't need to use energy because there's gravity. That's the natural force, that's the natural pull. But if I want to take something, I want to elevate something, you want to fly a helicopter or you want to go up the stairs, that needs energy because you're going against gravity. So concentration gradient, or the concentration, is the gravity in the body. Okay, so if there's a higher concentration on this side than this side, then there's a force going this way. You see, that is like the gravity. So you don't need to use energy. So if these ones follow this force and go this way, then they don't need to use energy. That's why it's passive. Now we call it here simple because this is able to go through the membrane, because they're usually fat soluble or lipid soluble molecules. Okay, so no energy is required because it's using the concentration gradient force. Okay, now because it's going through the membrane, there's no carrier, right? It's not using a channel, it's not using a carrier, right? A carrier is something that will transport molecules from one side and then move to the other side and deliver it here. So it's not using those, it's just going simply through the membrane. This means it cannot be saturated. What does that mean? That means the more I give on this side, the more that will appear inside here. So if I give 10 here, then 5 of them will go into here to balance it out. Now you have 5, 5. If I give another 10, it'll keep increasing. Now you have 10, 10. So that means, for example, if the chemical is toxic, it could kill someone. It could really harm someone, because that means there's no limit of how much could enter into the cell. It's just going to keep going in. As long as you're giving more, it's going to keep entering the cell. There's no saturation. It could enter into the cell from the membrane. So examples of this are lipid soluble substances like gases and some lipid hormones. Cholesterol, so fatty substances. And gases are considered somewhat lipid soluble. They could pass membranes. Okay, now let's compare that to this one here. And this is basically facilitated diffusion. Okay, So facilitated diffusion is still under passive transport because there's no energy used. So what does that mean? It's using the concentration gradient. That means it's going into the direction. I have two images I drew for you, so let's just use one of them for now. So that means it's using the direction of movement of the molecules will follow the concentration gradient. So that means it doesn't need to use energy. So here is higher, here is lower concentration. So the movement is this way, and these molecules will move this way. So that means it doesn't need to use energy. It's going with the flow, okay, of the energy of the forces. However, they can't pass through the membrane because they're not lipid soluble. So they need a protein carrier or a channel. They need to go through these channels. That means there's doorways for them. So let's say this is calcium, let's say, okay? And let's say let's imagine there's 3 calcium channels on the membrane. There's only 3 doors. Well, if those doors are full and there's a lineup, then not all the calcium can get to the other side easily, okay? So what does that mean first? So let's start from the beginning. Facilitated diffusion. It uses the concentration gradient, so no energy required. But since it needs a carrier or a channel, that means it can be saturated. And this is an example of basically these ions, potassium, calcium, or sodium, okay? So imagine that you have another example. Let's say you have a carrier here for calcium. Let's say there's only 3 of them on the membrane, even though maybe there's more or less, but most likely more. But imagine there's 3. So that means if this is transporting calcium from here to here, and this is transporting calcium from here to here, and this is transporting calcium from here to here, that means that these taxis are full now. So they cannot be used. So even if you add calcium to this side, the calcium has to wait. It can't get inside yet. So it can be saturated. The system to transport this ion from one side to inside the cell can be saturated, can be full. However, with simple diffusion, it could never be full because it just goes through the membrane. However, both of them are considered to be passive transport because they don't use energy. The third one is active transport. So this goes against the natural forces. This is like going upstairs, taking an elevator, flying up. So you're going against the forces of concentration, right? So the cell is actually trying to take things from a lower concentration and pumping it into the direction where there's higher concentration. Don't think why it's doing this. It's doing this because that's just the physiology of how it works and how we keep our physiology balanced. Don't worry about it. There's no reason to know why, but this is what's happening here, okay? And basically, we'll talk about the pump. So here, it's active. So since we have the forces, because these are more here, and these are less here, the forces go this way. However, this pump will try to push it the other way, you see? So it's the natural force is actually going this way because of the concentration gradient. However, this pump, for example, will take this and move it inside. That's its job. So since it's going against the concentration force, it has to use energy. It's hard work, okay? It's like it's resisting, but it'll still try to push. And usually these are called pumps. So if you hear something called pump, like sodium potassium pump, it means it's using energy and it's pushing things into the opposite direction of their concentration. Okay? So that's called active transport. Okay? So an example of that is a sodium potassium pump. Okay? And you might think, well, you see, we'll take this later, but potassium is high inside the cell. Okay? And sodium is really high outside the cell. So from this piece of information, you should be able to know which way this pump works. Okay? So since it's a pump, it's taking things, it's what it's doing, it's using energy to take 3 sodium from inside and 2 potassium from outside, and it tries to put the potassium inside and the sodium outside. Okay? How do I know that for sure? Because it's using energy. Since it's using energy, it's pushing molecules into the direction where there's already a lot of them against the concentration. So it's pushing sodium out to where there's a lot of sodium, and it's pushing potassium in where there's a lot of potassium. So that's what this pump does. Okay. All right, so let's review. We have simple diffusion. It's a part of passive transport, so it doesn't need energy. So from higher concentration and lower concentration, the natural force is this way. And it'll just use that force to pass. So it doesn't need energy. Usually they're lipid-soluble molecules. So that means, again, they could go through the membrane. And since they don't need carriers, it's not saturated. The more you give on this side, the more that will appear on this side. Facilitated diffusion is also passive because it's using the direction of concentration. So if there's more here and less here, then it's going to use that force. It's going to use that flow, so it doesn't need energy. However, they're not lipid soluble and they can't pass through the membrane. They have to use a protein channel or a carrier, which means the system can be saturated because these channels or carriers could be full. Then the last one is the active transport, where the molecules are actually going in the opposite of the direction of the concentration gradient. So the concentration gradient is actually this way, but the pump here is working on moving things the opposite way of the gradient, which means it needs to use energy. So this one actually uses energy, needs ATP, needs a carrier, so that means it can be saturated. And an example is a sodium-potassium pump. Digoxin, for example, is a drug that blocks the sodium-potassium pump in the muscle, in the cardiac muscle. So this is something, just an example. Usually in our full course, we use these little hints so that it builds up and then you remember them when we talk about them in pharmacology. Okay, so we're trying to use some methods and techniques to help you learn things in pharmacology easier. Digoxin is actually a drug used in cardiac arrhythmias and mainly congestive heart failure to increase the pump of the heart. Okay. Now you have this concept of filtration. I'm going to give you the definition. I don't say anything that much important, but it's basically the movement of water-soluble molecules along with the flow of water across the cell membrane due to hydrostatic pressure. So water could create pressure. So imagine there's a lot of water out here and here's a cell. It creates all this pressure that kind of leaks in. Okay, imagine you have some sort of, just clothing, right? Usually if there's something that could penetrate through the membrane because it's a lot of pressure. It might have its own channels, but I actually didn't look into that. But mainly the concept here is, along with the water going into the cell, some molecules are water soluble, may also pass through. This is called filtration. So the molecules must be small enough to pass through pores in the membrane. So there's actually tiny pores that maybe the water gets through, and along with it, some molecules go through it too. So here's again the membrane. Water may seep through really tiny spots in the membrane from its pressure. That's called hydrostatic because it's just sitting there and it's causing this weight and it leaks in. As it leaks in, some molecules are very tiny in the water, pass along with it. Large molecules can't. It gets stuck out here. That's why it's filtration. So larger molecules get stuck out and small ones kind of pass along with the water. Then we have one important concept is osmosis. Okay, so instead of putting in a separate video, I'm going to talk about it along with this video as well, because it's some sort of membrane transport as well, but for water. So imagine now we have scenario 1 here. So imagine we have our membrane. See this membrane? I try to make it look like the cell membrane, but I squeezed it up a bit. And as we said, we took all the transport things with the molecule. So the molecule, if it's simple diffusion, it could just go through. If it's facilitated, it needs to go through a channel. If it's active, then it's going to use a pump, right? So where's the concentration gradient here? Well, you have more of these here than here. So the concentration gradient force is going this way. Okay, so that means these molecules are going to try to go this way. However, if I created a membrane, or if the membrane does not allow these molecules to go through, okay, at this moment in time. Let's say there's sodium, but the sodium channels are closed, right? So let's say the sodium doorways are all closed. So that means they can't pass through. So what happens is the water will go into the opposite direction, right? Because the goal is not the quantity. Remember, it's not the number of molecules, it's the concentration of molecules. So the water will go from this way to this way, leading here to higher level of water, right? But the concentration of this molecule to the water is equal to the concentration of the molecule on this side to the water, okay? So the density or the concentration, what we call it, is the same. So this is called osmosis, okay? So back here, we're talking about movement of molecules from one side of the membrane to the other. Now we're talking about if the molecules at that moment cannot move to the other side, what happens? Well, the water moves to the opposite side to control the concentration. So if the molecules, again, I'm going to repeat it, if the molecules cannot move from here to here, the water will come over here to fix the concentration and make them equal. The body is always going after balance. This is called osmosis. It's very important to understand. It's the movement of water from one side of the membrane to the other to fix the concentration of one of the molecules, if the molecule cannot actually move itself, okay? All right, so that is it for osmosis.